Welcome to Amped Up, Utility Insights, Trends and Challenges. I'm your host, Melissa Parvis, CEO of Athena, a consultancy and workforce solutions provider operating in the utility sector. In this podcast, we explore the ever-changing landscape of US electric utilities with great minds and insightful conversations. Today, we have a very special episode. We're going to be talking about technology and innovation. We'll be exploring the latest advancements in technology in the industry on a macro level, which will include AI and energy generation technologies and just generally what's next in the clean energy revolution. I'm very excited to announce today's guest, Peter Kelly-Detwiler, who is one of the most knowledgeable voices in the industry. As a former Senior Vice President of Constellation Energy, Peter spent 15 years of his career in the retail energy space, shaping the industry in very remarkable ways. He spearheaded the creation of Constellation's demand response unit, growing it to a powerhouse of 800 megawatts of dispatchable load. In addition, he also led the development of VirtuWatt, which is a real-time energy use and automated load control platform, which still acts as a benchmark in the industry today. In addition to his executive leadership, Peter is also a prolific writer, having written for Forbes.com and other publications where he offers sharp insights into energy markets and forces driving the sector forward. Today, we'll tap into Peter's deep expertise to discuss the latest advancements in electric generation technology, from groundbreaking innovations to challenges of integrating these technologies into existing systems. So this is definitely a conversation you don't want to miss. Peter, thank you so much for joining the show. It's a pleasure to have you here.
Thank you, Melissa. Thank you for having me.
So let's kick things off. What interests you about these technological developments, and why is this such an important topic?
Well, we're sitting here at the end of the first quarter of the 21st century, and we're at this interesting inflection point where humanity recognizes that carbon, methane, carbon dioxide, etc., accumulating in the atmosphere is a big issue, and we have to therefore retool our global energy economies, and that's not easy. And that involves changes in behavior, but as much as anything else, it involves adoption of an application of new technologies and exist in addition to the ones we have now. And so, as I look at this as sort of an observer in the space, my question is, how quickly first of all, how do we develop these technologies? How do we overcome some of the challenges that are inherent in new tech? And then how do we adopt them as rapidly and effectively as possible as a human species?
I wanted to start off this conversation myself with a recent report written by the National Renewable Energy Laboratory.
Mm-hmm.
They were basically making a very interesting point that we have enough solutions to the problem. We already know how to fix it. And the way that we can solve it is by taking mature wind and solar markets in certain areas of the country, connecting them with areas that have a large load demand with very high voltage, long range transmission. And apparently, in their eyes, it was the cheapest way, the easiest solution to get low-hanging fruit for the decarbonisation efforts and the clean energy revolution. I have my own personal criticisms of this idea. To me, it seems like we're just sticking to what we know. Let's just do what we've always done to solve this problem. Apparently, it's the cheapest way of doing it. I don't know about that because I know long-range transmission is very expensive. In addition to that, they're saying that it's the best customer value. The customers will see the best value on their bills. I don't know about that. They probably have a lot of reputable sources and calculations that they're performing to back that up. But I wanted to hear your thoughts on those claims.
Yeah, NREL, which is what I call them, they do some really interesting work, and I rely on a lot of their reports. But I think that, and theoretically, I think what they're stating is true, assuming, first of all, that you could continue to build out solar and wind at relatively rapid paces. And then secondly, that human beings would allow you to string more wires and poles across the landscape. And what we've found,
Good point.
there's a tremendous amount of resistance to new transmission. Why? Because essentially you're taking electricity from state A and you're going across B, C, D, and E to get over to F and G. And B, C, D, and E say, what's in this for us? Now we have more unsightly wires and poles going across the landscape, eminent domain, all that fun stuff. And so typically what we see is anytime there's interstate transmission, the public utilities commissions and governments and sometimes counties in those middle states just say no, we don't want it. And they've been effective at doing that. So it's NIMBY, not in my backyard, but it's not in my state. There are some ways around that. For example, utilizing railway lines because there's a single right of way owned by one company, or potentially going along the highways of the United States. Each state owns the right to its own side of the road, but no one's really effectively solved that problem. So yeah, big picture, you could have a situation where you have an area where the wind doesn't blow for a little while, or they've got 4 or 5 days of rain and the solar isn't producing as much, and then you'd import from someplace else. The reality is that's going to be really hard. And there's also some other things we see. For example, let's jump over the pond to Europe. Right now, we see Germany connected to Norway and Sweden. And Norway and Sweden have enjoyed low power prices, but now they're connected by transmission. Now, what happens when Germany runs into an energy shortfall is it pulls more power from Norway and Sweden. Guess what happens?
Yeah.
Their spot market prices jump up, and now they're paying higher prices for something that had nothing to do with their grid. So if you did this in wholesale markets, you could also see these same sort of political issues and economic issues jumping into this as well. And then finally, there is this issue of energy droughts, long-term energy droughts. And national labs have looked at this and said, well, what is the likelihood of having 3 or 4 or 5 or 6 days of an atmospheric river, such as we've seen in California in the past, where rain comes in and reduces the output of the solar panels by, half or more? Well, it's not such a big deal if solar only represents 15 or 20 or 25 or even 30% of your energy output. But once you've got a lot of wind and solar in the mix and you're relying on it that way, now that could be a problem. In Texas and the Southwest Power Pool, less than 2 years ago, they had over 50,000 megawatts of wind installed. Maximum, it could generate 50,000. There was one period of time where combined, those two power pools generated about 300 megawatts of wind for an hour or two. So you need a whole heck of a lot of transmission coming from other places to balance that out. So
I see.
therefore, there's a challenge there. You certainly need to add more storage. Right now, we rely on, gas and other resources to fill the hole. But those are some of the issues that are inherent with that kind of solution set.
Right. And I've also prepared as well, in addition to that, a source from the US Energy Information Administration that shows all of the generation mix in 2023. And you can see that the vast amount of states are using natural gas, using coal, some are using nuclear. Very few are using renewable sources like wind or hydro. And I don't even think solar is on the map. Yeah, this idea of just using existing technologies to support the clean energy transition, from what I'm seeing, it doesn't really seem like it's a viable solution, but I'd love to hear what you think.
Well, sure. I mean, if you think about that, you could do the same thing with the transportation fleet and say, look, 98% of the vehicles out there are internal combustion engines, even though we sell 10% EVs each year. Why? I mean, because essentially you've got a lot of inertia built into the system where every car you buy lasts 14 years or 13 years before it ages out. So even if tomorrow every new car sold was electric, it would take 12 or 13 years for the whole fleet to turn over. Same thing in the power grid. You have all these investments in nuclear plants and gas plants, etc., where some of the nukes now are older than I am. And the gas plants, they typically last 30 or 40 years. So even if tomorrow, you had a magic wand and said, we're going to put solar and wind in everywhere, well, you could do that, but you would have all these stranded assets, resources that you built, gas-fired generation that wasn't fully paid for yet.
I see.
So there's all this inertia built into the system as well, financially. There's also another issue, which is inertia physically. In our grid, we have a 60 hertz grid. That means that in our alternating current, there are 60 oscillations per second, and it's kind of like a human heartbeat. You have to have 60 oscillations per second in order for the grid to be healthy, for stuff not to break. If the grid drops down to, say, 59.2 or 3, which it did during Texas during Winter Storm Uri, it did that for about 4 minutes. If it had stayed at that 59.2 range for another 4 minutes, the entire grid would have collapsed. Now, how do you maintain that frequency? Well, one of the things you do is the spinning rotating masses of metal in our power plants, like our steam plants when we burn coal or fissile material in a nuclear plant, it actually creates steam that spins a turbine that rotates at multiples of 60. So it's either 1800 RPM or 3600 RPM. Now, and essentially when you have under frequency, you actually slow down those rotating masses of metal, and inertia is released into the grid. For 2 seconds or so, extra power goes into the grid. So in case something happens real fast, it can manage that frequency. Then other resources have to come in behind it and manage frequency for longer periods of time. You with me so far? Okay, so and gas turbines also spin. So those rotating masses of metal create physical inertia.
Yeah.
That manage the health of that grid. Now you retire your coal plants, your nuclear plants, your gas plants, you've got this issue of inertia that you still have to deal with. So you can put in things like synchronous condensers, which are kind of like a rotating flywheel, or you can start to use the inverters, which are the devices that connect solar and wind to the grid, and they can sense inertia and create so-called synthetic inertia. But it's still a challenge and something we haven't entirely solved. Batteries can help too, but it's another, the grid is economic, yes, but it's also dictated by physics.
Wow. I've
Yeah.
never heard of anyone talk about that before.
Yeah, yeah.
I
It's
listen to a lot of renewable energy podcasts, and no one's ever mentioned anything like that.
Oh yeah, synthetic inertia is big. They finally, in Australia, they now have 2 batteries. The big Hornsdale Reserve one that Tesla first put in, remember? He said in September a few years ago, if I don't have this built by December, it's free, it's yours. Well, that first was meant to back up wind, sort of bigger picture. Then they taught the battery essentially to bring inertia to the grid. And then an Italian company put a battery in there just to provide inertia into the grid. So yeah, it's something one has to think about as you change the resource gen mix.
Wow. I guess later on the podcast, we'll talk a little bit more about that, about how to solve that issue. But for now, I'd like to turn the conversation to a little bit of a different direction, but very topical. How do you see AI is informing the acceleration of new technology?
Yeah, there's 3 ways that's happening. First of all this massive data center load that's coming in is dwarfing the available resources. So what does that mean? Especially companies like Google and Meta and Microsoft that have made commitments to sustainability. Well, it means they have to find and support new carbon-free resources. So it's not an accident that these big data center companies are making investments in modular nuclear in companies like Kairos and Oklo and NewScale and others, where they're saying, we'll take 800 megawatts of offtake by early 2030s, that sort of thing. So only deep-pocketed companies that can afford to pay a lot and have some patience can do that sort of thing. So they actually could drive new tech on the supply side. One of the other interesting things, Google, for example, has made a commitment to a company called Fervo. And Fervo does this enhanced geothermal. So typically we think of geothermal on the Ring of Fire. There's, steam and hot rock coming out of the ground like in Yellowstone or where there's volcanoes, and you drill down and you tap into that hot reservoir of water down there. Well, this goes deeper than that in many instances. They go down like a mile using fracking tech. Then they drill sideways 2 wells that go down vertically far from each other. Then they sense and move towards each other and finally connect. Then they smash up all the rock with fracking technology to create surface. And the rock is hot. It can be over 400 degrees Fahrenheit. Now you take a heat transfer fluid, could be water, pump it down there, get it super hot because it's in contact with all the multiple surfaces in the rock that you just fracked up. Bring that water back to the surface. It boils, creates steam, pressure, spins a turbine, generates electricity. So Google, through Nevada utility NV Energy, has a contract for 115 megawatts of enhanced geothermal. Meta has made a commitment to do something similar with a company called Sage Geosystems. So you can see some of these, again, the big data companies pushing new tech to support their AI language learning models. Now, that's one part of it. The other part is the grid, fundamentally, we have to go back to the chemistry and the physics. What are we doing? We're moving electrons around at the speed of light through the grid and keeping it all in balance. Now, fundamentally, the grid then is a function of materials science, stuff, right? battery chemistry, LED lighting, other technologies, solar panels that become more efficient. Most of the time, this is a material science question. How better to accelerate material science than to use supercomputers? So I went to Lawrence Berkeley Labs for my book before any of these new AI models were out there. And I went to see a computer that could only do 14 quadrillion calculations per second. Now it's the successor computer can do about 5 times as many calculations per second. And you can ask it, for example, I want to make a better battery that can charge more quickly, or some other characteristic, longer duration, something like that. And then it will go into the periodic table and combine all the different elements in the periodic table and come back to you with theoretical compounds that have never existed in the history of the world. So the challenge is now you have to make these things, you have to synthesize them. So you can use robots to inform that process as well. And robots combined with artificial intelligence, not only do you record your successes, but you also record your failures. And then that's mineable data for AI as well. So there's a great likelihood that we could accelerate the process of inquisition in material science to make better things all across the grid, whether it's insulators, whether it's conducting material, whether it's solar panels, batteries, and so on and so forth.
Wow.
Then the last piece of it is the distribution side, where we use our power. Typically, your average grid is supersized for that hottest day of the summer when everybody's using juice, and we're all making ice and refrigerating, our air conditioners are on even as we leave the doors open. And the rest of the time, we're not using that much electricity, but we guarantee that everyone's going to have power, and we plan for one loss of load event every 10 years. And so what that means is that on average, the grid is utilized at a 42% capacity factor across the course of the year. If we could bump that up to 43, 44, 45, 46, 47, whatever, we'd actually flow more megawatt hours, gigawatt hours, terawatt hours over the same infrastructure, which would lower the per unit cost. How would you do that? Well, once you have a grid that has things like water heaters on it, where you could actually heat the water during non-peak periods of time, or you got batteries in people's garages where you can absorb a whole bunch of solar energy during the day and then release that energy in the evening to meet the peak demand, or charge your electric vehicles again during the middle of the day, what I call affectionately tummy tucking the duck, because you take that duck curve when there's all that solar in the middle of the day, absorb that, and then you actually have batteries now in trucks and mostly in buses at this point in time, in some vehicles like the Ford F-150, that can be programmed to release energy back into the grid during periods of higher demand. And so you can, now, how do you do all that without intelligence? You need that supervisory intelligence. You can have a company here doing it at a company there, but if you want to bring this en masse and really harness AI to create efficiencies in the grid, that's understanding what's happening, where it's happening, how much of it is happening, how long is it happening, and what value is it creating for society. Only artificial intelligence can handle a problem of that magnitude, because a utility like Pacific Gas and Electric, they speculate they could have 20 million interactive devices on the customer side of the meter at some point in the future. So that's a huge data problem. So those are, again, the three things. So data centers driving new generation tech, then material science, and then finally efficiencies informed by more intelligent supervisory capabilities. Those are the three main areas that I see. Of course, then there's a whole bunch of other smaller use cases.
Right. So even though a lot of people, unless they look into it, might not hear about it, there's a lot of new technologies coming out. But my question to you is, what decides the viability, the commercial viability of these new technologies? How do they decide what thrives and what dies on the vine?
Yeah, that's a really interesting question. It's one that's been going on since the history of economics. Typically, a way that a new technology survives, first takes root, is it finds a value proposition. So let's look at solar, for example. The first place solar found scale was in Germany, even though Germany's pretty north. It's Montreal type north, It's not the most solar saturated place in the world. But in Germany, they wanted to accelerate solar, so they were paying people about 40 cents a kilowatt hour for putting solar on their roof and exporting it back to the grid. The market was big enough that companies started to form, and then Chinese companies came in and started buying a lot of these German companies and sort of putting them on steroids in China because they wanted to get into the marketplace and also create jobs and so on. Now, that was still sort of an artificial program there. Then in the US, we had subsidies in places like Massachusetts. We have so much solar in New England that yesterday morning, for example, there was less demand for other generation in the grid at 1 o'clock in the afternoon than there was at 4 o'clock in the morning when most people are asleep. But you find there, absent subsidies, you find the highest avoided costs. So for example, if I have a new tech that's efficient or is going to replace some other source of generation, I almost always would go to an island economy. Why? Because islands have to import fuel, usually coal or fuel oil, which is really expensive by the time it gets there. So instead of having 10 cent a kilowatt hour electricity, it could be 30 or 40. Therefore, if I'm displacing it, my value proposition is way better in an inherently inefficient economy like an island economy. Then I scale, I build my business models, I refine them in those high priced environments. Once they get better, now I take over the mainland, if you will. Right?
Mm.
And so that's how tech adoption often works. You find those highest value proposition use cases, and then you get in there, you sort of take root, and then you refine, make the tech better, make the business models better, and drive your costs down and scale and move out into other markets.
Mm. Yeah, that makes a whole lot of sense. You mentioned earlier about long range storage being super important for the grid, for the viability of the grid. Could you go into a bit more detail about what the deal is with long term duration storage?
Sure. So, first of all, today we have enough solar in some markets that in the middle of the day, like in New England or in a place like California. In California last year, there were dozens of days where the need for any other generation besides solar was zero, right? So essentially, in fact, some cases, prices go negative because you have so much solar and you still want to keep your gas running for things like inertia. Yeah, so you keep the
Mm.
turbine spinning, but they have to get rid of the power, so they pay someone to take it. So there's 3 or 4 hours in these solar saturated markets where prices go really, really low. And then as soon as the sun goes down, there are 3 or 4 hours, usually from 3 o'clock or 4 o'clock in the afternoon to 8, 9 o'clock at night, when prices are double or triple what they are in the low part of the day with all the sun. And so now you add 4 hours, 3 or 4 hours of storage. And with lithium ion batteries, you lose about 10% of the energy in the round trip efficiency. So you basically lose 10%, but you're tripling your money charging, discharging every single day. So you can solve for the 4 hour thing. But then as you add more and more renewables into the mix, you start to have to increase the duration of the storage that you're bringing because you need it for reliability reasons. Sometimes 4 hours isn't going to be enough. So you start to see players like flow batteries. They come in. Flow batteries have massive tanks of electrolytes on each side of a membrane. The membrane is sized in kW, kilowatts, or megawatts, instantaneous draw. And then if you want more energy, you just add more tanks of electrolytes. So now you can do 8 hours, 10 hours, 12 hours, and there's an economy of scale there because the membrane's the expensive part and the electrolytes are the cheap part. Unlike lithium ion batteries where it's like Lego blocks, you want to add more length, duration, you have to add more blocks. There's no economy of scale. So flow batteries enter into the game. Then you can do things like you can compress gas. There's air. There's a company in California pushing a whole bunch of air down into a cavern that's purpose built with water on top of it and a membrane to create pressure. And they'll put that down there. And when they want energy, they basically start to let the air, the compressed air, flow through a turbine, spin the turbine, generate power. They can do, say, 10 hours. Then there's other companies. There's one called Highview Power in the UK. They liquefy air, ambient air. And by using compressors to cool it down, liquefy it. When they warm it up again with the waste heat from the compression process, that air expands in volume by roughly 700 times, creating pressure that spins a turbine. Now they have about a 60% round trip efficiency, maybe 70% RTE, round trip efficiency. And so they can do like 12 hours of duration. There's liquid CO2 companies. There's all sorts of different companies. There's a company that liquefies silicon at 1400, 14 degrees centigrade. and stores that liquefied silicon in tanks that are highly insulated. And then when they want electricity, they use that heat to boil water to spin a turbine to create electricity. So there's all different kinds of ways of doing it. Then there are some new emerging battery technologies like salt-based batteries. So lithium-ion battery, typically you can charge it 2,000 times. So 7 years before the battery is effectively no longer commercially viable. With these new sodium batteries, you can charge them 50,000 times, which means I'll be dead before that battery's done charging.
Mm.
Right? 50,000 cycles is forever. Uh, and then you have, and those are going to be relatively cheap because it's salt. No lithium, no cobalt, those sorts of things. Then
Are
you
those available today?
China is just putting them into vehicles now. They've put their first grid storage projects into the ground last year. And in this country, our first gigafactory for salt-based batteries is going into Georgia right now. We don't know exactly how large it is, but they've made their first announcements, and it's like a multi-billion-dollar investment. And they've also proven with the sodium batteries, they can take an existing lithium-ion manufacturing line and retool it relatively quickly to make sodium batteries. So it's a semi-mature technology right now.
Mm.
And just like lithium-ion batteries, the job's going to be to scale it to drive the cost down, which is what we did with lithium-ion batteries on the grid. First of all, we put them in millions of cars, and that drove the cost down. In fact, I read one time that Tesla's Gigafactory manufactured those batteries that are, they look like this, the little double C's we have, or double D's. They shoot these out faster than a machine gun shoots out bullets. That's how fast they manufacture them, right? And so that's scale. So we have to bring that same sort of applied scale to solar. Okay, but the one I'm probably most excited about is called Forum Energy, and that was this Matteo Jaramillo, which was the CEO. Well, no, I'm sorry, he is the CEO of Forum. He was one of Elon Musk's battery guys at Tesla. He was the lead battery guy. And he foresaw that the grid was going to need this long duration storage to deal with these issues around renewable energy droughts and the value there. And so he and his team separated off, he separated off from Tesla, put a team together at an incubator lab here in Massachusetts in Somerville, Greentown Labs, and they started researching all these different chemistries. They knew what these things could generally do, but they went into greater detail. And one of the things they were looking for was low cost, and another one was long duration. And ultimately, they settled on something that Neil Young knows: rust never sleeps. And so what did they do? They created these little golf ball sized pellets of iron. And when iron rusts, when it oxidizes, it releases energy. And so they were able to harness that energy, capture it, and deliver that current. Now, you have to derust that ball in order to do the process again, to lather, rinse, repeat it. And so they figured out how to do that. Now, the beauty of this technology is you put them, first of all, it's iron, so it's super cheap, right? We have iron everywhere.
Mm.
And so they located their factory in Wyerton, West Virginia, steel country, and it's right on a river, so they can move iron in, and then they can move these batteries out, which are heavy because they're washing machine sized containers that are stacked on top of each other. But the beauty of their storage technology is it's rated for 100 hours. And so you
Oh,
4 days of storage,
yeah.
right? So like if you're one of the data center companies and you want to have wind and solar and reliable energy, I foresee it would really surprise me if within the next year we do not hear one of the big data companies saying we have a relationship with Form and some wind and solar because we're going to take all three of them together and use the Form energy battery to peanut butter over any of the gaps between the wind and the solar and deliver dispatchable energy. Like, I think that's one of the next logical, inevitable things to happen. This is a 500 megawatt factory capable per year, capable of delivering 500 times 100 megawatt hours, right? So it's big.
Mm.
And it's already fully subscribed, as far as I understand it, for its first year of output. And now they're expanding the facility because the demand is there. So the first one of these goes into Cambridge, Minnesota this year for just like 1 megawatt, 1,000 megawatt hours. And then Georgia Power's got a 1,500 megawatt hours. And, and then there's a whole bunch, then there's one in Maine for, I think it's it's like 85 megawatts and 8,500 megawatt hours to keep because there's wind that's stuck behind transmission constraints up there. So there's been all these announcements of these foreign batteries that are going to go into the marketplace. None are there yet. We don't yet know how quickly the cost curves are going to come down, and the faster those cost curves come down, the more easy it is for everyone to buy these things and adopt them. But if this thing goes the way many people hope, it could be a pretty significant solution. There's one drawback.
Mm.
The round trip efficiency is somewhere around 40%. We don't know the exact numbers. I've seen one presentation from them that said 40, another said 45. So you're going to lose more than half the energy. But if you've got super cheap wind or super cheap solar,
Yeah.
then really maybe that's not so much of an issue.
Yeah. It sounds, there's so many revolutionary technologies that are coming down the pipe or even being implemented now.
Yeah.
But unless you are Peter Kelly-Detwiler and you spend the majority of your time reviewing and researching and finding out about these things, I've never heard of this. And I'm 99% sure that 99% of the layman population hasn't heard of this. In addition, the most listened to podcast in the world, God, what's his name?
Joe Rogan?
Joe Rogan, thank you. I had his picture in my face. Yeah,
Yeah.
Joe Rogan. Every like 5 or so episodes, he goes on a little rant, right, about how unuseful wind and solar technologies are, how they're rubbish and they're never going to work and they're never going to be able to really be rolled out long term. And it's just spreading misinformation. And I find it so sad. Why are these companies not able? These amazing companies that are doing amazing things. Why are they not able to communicate and get their information out to the public so that people know there are alternatives coming down the pipe and there are solutions to these problems?
Yeah, I think in some cases it's the wariness of an untried technology that's not in the field yet. And certainly we've seen things sort of blow up on the launch pad, if you will, right? So, Solyndra, for example, that classic solar panel failure from years ago. So I think it's one of these things where people are just a little bit cautious about announcing things before they're ready and before they're commercially in the field and the cost curves are set. But I do, back to your question or your comment there. One of the things that really frustrates me as an observer of the human condition, and sometimes I imagine I'm not a member of the species, I'm just trying to figure out whether these idiots on two legs are going to survive or not, as if I weren't one of us. And one of the things that drives me absolutely nuts is when people take a snapshot view of something.
Mm.
See, this thing doesn't work, therefore it's a failure. If we'd have done that the first time the car missed a horse and went off the road, we would have said, see that? Cars are useless. And people probably did back then. And then, of course, now people do the same thing with electric vehicles. See, that person ran out of charge after 200 miles. Well, they're completely not paying attention to the battery technologies and how quickly that technology is evolving and how fast it has already evolved. So what we were, to use another analog analogy, we're living in a motion picture world in which the frames are accelerating. We're actually living in a digital world, but let's stick with that stupid analogy. And most people fail to appreciate that or do not want to appreciate it because it doesn't serve their policy of misinformation. And that kind of, though, intellectual laziness where people don't look at the trajectory of things, both historically and where they are likely to go, that is, for me, makes me see red. Because that's not how
Mm.
the world works, and I think that does a disservice to people.
Yeah, that's a great point. And we're seeing it right now with AI. There's so many people that say, "Oh, it can only do this, it can only do that," and no, it can do lots of things already, and it's going to do a lot more things in the future.
Yeah, I mean, just ask them what could it do 2 years ago versus what it could do now.
This is the worst it's ever going to be,
Yeah,
and it's already pretty
exactly.
amazing.
Exactly. There's
Yeah.
a really cool book called Situational Awareness by Leopold Aschenbrenner, which is free online. And he's got one chart in it that shows ChatGPT 3.0 and then I think 3.5 and their ability to take the SATs, the LSATs, the GREs, and so on. And they were in the 40% range relative to human beings. And then a year later, they were in the 80 and 90% range in just a single year because the LLMs, the large language models, got that much better. And again, so it's a snapshot view, which, you know,
Yeah.
I don't know
Yeah.
why you and I aren't rich and the rest of the world poor if we're smart this way. Why do we keep making bad investment decisions?
Very
I'll
true.
speak for myself, you know?
Very true. I'd love to talk a little bit more. You mentioned it earlier about small modular nuclear reactors. That's something that I don't really know much about, and I'd love to learn more about what they are, how they're different to other nuclear plants, and what solutions they're bringing.
Sure. Okay, so let's start with the big ones that we know of. The light water reactors like Indian Point or 3 Mile Island are the ones that, supply what, roughly 20% of the electricity in the United States. Most of those were built in the 60s and the 70s. And back then, a lot of them were built at the same time. And we had a lot of people coming out of Hyman Rickover's nuclear fleet, all the nuclear submarines and the aircraft carriers and so on. So we had tons of engineers. We still do, but we don't train that many people in schools like we used to. Well, so what happened after 3 Mile Island is we weren't building many more nuclear plants. And so the skill sets started to dissipate and the expertise in building the stuff, not just managing it, but building it. So then we start to see this new nuclear renaissance was supposed to happen. The Levy plant in California, the in this country Vaughtle, and then the VC Summer plant, and some other ones. So what happened? Okay, so let's start with the Levy plant in Florida. It started off with a price tag of $4 billion, and by the time they decided not to do it because of cost overruns and inflation and so on, it was up to $16 billion, at which time the utility had already spent $1 billion in planning, which it made the ratepayers pay for.
Mm.
Then let's look at the VC Summer plant. This thing was in South Carolina. They're now looking at revitalizing it, which strikes me as astonishing. But that thing, they finally pulled the plug based on Public Utilities Commission staff recommendations and others after $8 to $9 billion was expended, making it the most expensive hole in the ground because they kept on having cost overruns. Now let's look at the Vaughtle plant, the Alvin Vaughtle plant in Georgia. That thing started off at a price tag of $14 billion and ended up bankrupting Westinghouse and ultimately costing roughly $34 billion. Now the question ultimately is why? And the answer is, and there's a great book about why it's hard to build big things. The answer is the same reason the big dig here in Boston, which was putting our highway underground, went from like $4 billion to well over $10 billion. Because these are very complex projects that are sequential. So B can't happen until A is done, right? And so you have all these processes, all of which also require some supervisory oversight, a lot of regulatory oversight for good reason. And so every time there's a delay in X, everything downstream from that, well, the meter's still running. The contractors have delay penalties in their contracts and so on and so forth. So the costs keep going up. It's not just in this country. Now, in the UK, the Hinkley C plant is way over budget. And the plant after that, whose name I forget, the most recent price tag was $40 billion. And then in Finland, the Olkiluoto plant went way over budget. France's Flamanville did. The only people who can do this well right now appear to be the Chinese and some of the other East Asian, countries. Now, so in this country, big nuclear is probably dead. But enter the little guys.
Mm.
What's so great about a modular nuclear? First of all, with a big one, like what we have in this country or what we had in Japan with Fukushima, is and also what's going on in Zaporizhia in Ukraine, Europe's largest, the plant has to be cooled all the time. Even if it's not running, the fissile material is still going, right? And so when Fukushima happened and that tsunami came through, the plant shut down. So it wasn't capable of cooling itself. But all these plants have backup generators in case there's an event to continue to cool the plant and manage the heat from the fissile process. In Fukushima's case, that wave also took out the backup generation. That's why they had the issue there.
Right.
In Ukraine with Zaporizhia, that plant, they have to bring diesel to it to the backup generator all the time. And sometimes the Russians are interdicting the supplies of fuel. And so there have been a couple times in the last 2 years when it's been a week away from meltdown because if they weren't able to get more fuel to it. Okay? So these are the sorts of things that are inherent in the current design. When you go to modular, there's some really interesting designs. For example, there's one where you have a salt plug at the bottom of the reactor vessel. And the salt plug is essentially only kept in a solid form by fans that are run by the nuclear generator. If the nuclear generator stopped running, then the fans would stop and the salt would melt from the heat in the generating vessel and all the material would fall through into a secondary container and be rendered inert. So it's inherently fail-safe. So there are these safer designs that can help with some of the modular reactors. But the interesting thing around them as well is you build them in a factory. I live in a modular home. Nobody knows it because of the way we designed it, but if you drive by a home that someone's built that's stick built, you see, the windows can be off a little bit and it's exposed to the elements when you're building it. The quality control isn't as good as modular because it's all on wheels moving around inside in a factory.
Mm.
Same thing with modular nuclear. You make all the pieces in a factory on site. And the goal is to make dozens and dozens of them so you can drive the cost down. But you can
Mm.
manage all the QC in the factory. Now, of course, then you ship it to the site and you have to manage QC as you assemble it, but that's more of a Lego building process to oversimplify it, right? So the goal is to make these things as small as, say, 10 megawatts, which is pretty tiny, to as big as 300 megawatts, which would be about a third the size of a normal nuclear reactor, and build them a lot faster. And if you think about it, we have had modular reactors for decades because that's what's in every nuclear submarine
Yeah.
and aircraft carrier. We know how to do it. And so you've got companies like Bill Gates' TerraPower already building its site in Wyoming. It doesn't have approval for design from the Nuclear Regulatory Commission, nor does X Energy, nor does Oklo or Kairos. The only one that does is NuScale, and they've changed their size and their version, so they're going to have to get some revisions to the NRC approval. But one of the things that happened last year in Congress, this is a bipartisan issue, it's one of the few things both parties agree on, is that modular nuclear should move forward, and they are working to accelerate the process of permitting these designs. Now, so right now, there's some Equinix, for example, which is a co-location data center company. They've committed to, in an LOI, so it's not firm, but a letter of intent, 800 megawatts of Oklo machines, and then a lot of the other big data companies have also signed up with other people. It looks like around 2030, we'll see the first of these with steel in the ground. Certainly Poland's pushing ahead, Romania's pushing ahead. Canada's been pro-nuclear for a long time, and they'll probably locate one of these late this decade, early next, on the site of Darlington or Bruce, one of the nuclear plants that's already up there. So I think we're just about to see the possibility for a real nuclear renaissance with these smaller modular machines. The question's going to be, again, cost. The NuScale one, which is the furthest along in design, they had an agreement with an association of Utah municipalities for $58 per megawatt hour. Then COVID came along, supply chain issues, some other challenges. They revised the price to $89 a megawatt hour, and everybody pulled out. To put that in contextual, you can get electricity from like a gas plant for, say, $40, $45 a megawatt hour, and your typical power purchase agreement now for wind and solar is in the high 40s, low 50s. So these are, quite a bit more expensive. The question is, can we scale them and get the cost down?
Right, I see. So that's one limiting factor, but what other limiting factors are there? Why has it taken so long to get to this point?
Yeah, I mean, the other one is NIMBY, right? The siting's going to be easier in some places than it will be in others. It's going to be hard to put these near populated centers because people are going to still go, oh, nuclear, don't want it. And so that's part of the issue. And I think, the real challenge before that was gas had been so cheap for such a long time. And so gas-fired generation was cheap. And the first PPAs, when solar really scaled, the power purchase agreements were in the $25 range. Now they're a lot more expensive than that, but it was hard to compete against the other costs of other generating resources. Now that some of those costs are coming up, there's a little bit more potential room for profitability in that space.
We've talked about small modular nuclear reactors. It's really hard to say. I've heard a lot about nuclear fusion, and everybody's very excited for it. Could you briefly explain the principles of nuclear fusion and how it differs to nuclear fission? Try and
Sure.
say that fast three
Yeah.
times.
So splitting, with fission, you're splitting the atom and releasing energy. With fusion, you're actually creating a reaction with, for example, with hydrogen, where there is a fusion of the atoms and energy is released that way. And with fission, you have a situation where the container vessel is protecting all of us from the radioactivity and the fissile material. With fusion, the vessel, which is probably going to be a magnetic bottle, is actually meant to protect the reaction, the fusion reaction. So if something goes wrong and the magnetic bottle sort of falls apart, there's just helium and there's no real danger to humanity there. The challenge has been that up until recently, nobody had ever proven that you could get net energy out of a fusion reaction. But in Lawrence Livermore labs, a little over a year ago, they actually proved that. They put in 2 units of energy and basically they bombarded with lasers these little hydrogen pellets and they got fusion to occur and they net about 3+ units of energy out of it. Now, they had to put hundreds times more energy into the lasers to get it started, but that wasn't the issue. They wanted to prove that they could get a net gain from the fusion reactor. And then they had trouble replicating it, partly because it was difficult to focus the beam on it. But finally they figured it out, and now they've been able to replicate it a number of times. Okay, so that's proven. Now, there's billions of dollars going into this space, and one of the leaders right now is a company right here in Massachusetts in Fort Devens called Commonwealth Fusion. And they have this thing that's MIT and so on. Spark is what it's called. And they believe that they're going to be able to demonstrate their capabilities within the next few years. And they're actually talking about a demo fusion facility, a little one, down in Virginia, sometime in the 2030s, probably early 2030s. The joke with fusion has always been it's the power source of the future and always will be. But because of advanced computational capabilities in material science and just exchange of information, smarter scientists building on bodies of knowledge, we're getting closer to that and maybe doing it at a scale that's small enough that it can be cost effective. Remains to be seen, but it's more promising than it's ever looked before.
Right. So more cost effective, and if does turn out to be commercially viable, what other advantages will it bring?
I mean, could you imagine if this thing, back in the day in the 70s, nuclear was going to
Yeah.
be too cheap to meter? What if you actually could come up with an energy resource that you could locate anywhere that was relatively safe and was super cheap and super abundant? That would transform humanity. And so that's the potential promise of something like that, is it could be revolutionary in that sense.
Do they have a timeline on that, on when it'll either be rolled
Yeah.
out or not?
Well, I mean, it would be kind of cool. Okay, I'm 64. I'm hoping by the by the end of my lifetime to see some real advanced practices going on. If Commonwealth Fusion and others are right about what they can do, then maybe we'll see some of these things, the first ones in the field, working, proving up fusion within, I don't know, 10, 12 years. That's their goal anyway. And just in order for them to stay viable as companies, they have to continue to make progress so they can raise more money, so they can get closer to the finish line. So I think within 10 years, we may have a good sense as to whether or not this is real. Bearing in mind, though, I was writing for Forbes. I started writing in 2012. I think in 13 or 14, I wrote an article about Lockheed, and they had a tiny fusion reactor that could fit on the back of a truck, and they said they were iterating really, really fast, and they thought it was going to be commercial and commercially viable, and then poof, you didn't hear anything else about it. So, is skepticism warranted? Yeah, I'm Missouri. I'm the show me state. I want to see something really happen here, but at least my curiosity is piqued in ways that it wasn't a while ago.
Peter, I really appreciate this conversation. It's been extremely interesting and insightful. Finally, my last question to you is for our listeners, people who might want to know a little bit more about this information or get involved in this field. What would you suggest and what resources would you advise?
Yeah, so the first thing is I'm on LinkedIn and I have 42 newsletters that I read pretty much every day. I read 2 to 3 hours a day. You don't have to, but I've got them all on a spreadsheet. And if you just reach out to me on LinkedIn and ask for my list of newsletters, I'm happy to send that to you. And there's a couple that are my go-tos, and I've highlighted which ones those are. So that's a really quick way to do it. Then there's a great book on this called The Grid by Gretchen Baki that explains the power grid. She's an anthropologist, so she explains it, for your average reader. And then, I wrote this book, The Energy Switch, 4 years ago, which was my attempt to try and condense everything I was curious about on how the whole grid works. And some companies use it for all their new employees to help them get up to speed so that, the decades it took me, you can do it in a couple hours reading my book. It's time you'll never get back, but it might be time that's worth spending. So
That's awesome.
those are what I would suggest.
Thank you so much, Peter, for your time.
Oh, it's my pleasure. It's been a real privilege, and
Yeah,
it's certainly a quickly evolving space and super fun to be involved in. So thank you.
absolutely.
Thank you for listening to Amped Up. If you like this conversation, please support this content. Subscribe and rate the show on YouTube, Apple Podcast, or Spotify.